Vector Calculus, lecture 22. So again, the final exam is Monday, May 20th, 11:30 a.m. to 2:30 p.m. in Gillette 203. We have five more classes. And today we start chapter 17. And you might say finally, because this chapter is called Vector Calculus. And the course is called Vector Calculus. And it's taken us all semester to get up to this point. And in chapter 17, we cover the first four sections. So 17.1 is about vector fields. 17.2 is about line integrals. 17.3 is conservative vector fields. And section 17.4, I'll put this in cap letters because this is really the most important thing in the course, Green's theorem. Give this a star. This is really the combination of Math 226. So this is really what I want to get to. It's a very beautiful extension of the fundamental theorem of calculus, which you learn functions of one variable, now to functions of two or more variables. And since this is really just an introductory course in vector calculus, we're only going to consider functions of two variables, which is what the theorem is about, and not functions of three or more variables. So what have we looked at so far? We've looked at vector valued functions. So a function R from the real line, let's say, into the plane. So if t is x of t, y of t of the vector, and then this is curve. Right? If you look at this, say for t going from A to B, this is R of A. This is vectors, and you end up at R of B. So a vector value function takes a number or a scalar to a vector. Right? So the graph of this is a curve in space. And then we had functions of several variables. You might have a function z is a function of f and of x and y. So f was a function from two variables pointing the plane to r. And the graph would be a surface. So this is the surface. 3 space. That's what the graph of a function of two variables like. So for a vector valued function, you have a real number that's sent to a vector. For a function of several variables, you have a vector that's sent to a number, and a vector field is a function that sends a vector to a vector. So in two dimensions, a vector field is a function from the set of vectors to the set of vectors. So f apply the vector x, y will be vector in R2, And it has the first coordinate, f of xy, and the second coordinate, g of xy. So that's what a vector field is. That's really well studied in vector calculus. You could also write this as f of x, y, I plus g of x, I, j. Little and little g are functions of two variables. So we could have, for example, f of xy is the vector 2x, 2y. Or if you like, 2xi plus 2yj. So this means to every point in the plane, you assign a vector. So for example, f of 1, 1 is the vector 2, 2, 2. So at this point, you assign this vector 2, 2, 2. F of 2, 1 would be the vector 4, 2. So this 1, 2, 2, 3, 4, 5, 6. 1, 2, 3. So here's the point 2, 1. And that gets a vector which is 4 units to the right and 2 units up. Right? This is f of 1, 1. This is f 2, 1. If you take the vector f of 2, 2, 2, that's 4, 4. This vector field doubles the coordinates. So here is f of 2. A vector that's assigned to that is vector. 4 units to the right and 4 units up. So a vector field to every point in the plane assigns another vector. And to some extent, you can draw a picture of it. What are very, very important are what are sometimes special case vector fields, which are radial vector fields. A radial vector field sends every vector y. Let's go to this r. It's always in the same direction to some multiple of r. So a radial vector field is of the form f at x, y is some it's just right like this. Suppose that r vector x, y is sent to some multiple of this, and we often write this as the length r, which is a number to the p, or r over r to the p. This is a radial vector field. Radial vector field doesn't change the direction of any vector. It just stretches it or turns it around. So you have, again, you have this vector. The vector field sends it to vector in exactly the same direction, or on this line, but in the opposite direction. That's a radial vector field. And just a very special case of a vector field. So maybe just to get a sense of these things to do, I should write down some examples and try to sketch what they look like. So let me pick examples in the text. They usually come with very nice pictures. So suppose you take the vector field f of x, y is equal to 0x. or x times the vector j. This is sometimes called shear field. The vector fields come up all the time in physics and engineering. So it's just something that has to do with the fluid motion, but it's just the name. It's just give a name. But what does this vector field look like? So f of x, y is 0x. 0, 0 is 0, 0. That hasn't changed. Is f of 1, 0, 0. F of 1, 0, 0 is 0, 1. So at 1, the vector associated to the point 0 is 0, 0, 1. What f of 2, 0? 0, 2. So the vector associated with 2, 0, 0, 2. What is f of minus 1, 0? It's 0, minus 1. What is the vector associated with minus 2, 0? 0, minus 2. What about f of 0, 1? F of 0, 1 is 0, 0, 0. In fact, for any point on the y-axis, f of 0, y is 0. Just this. What about f of 1? That's also 0, 1. Here's 1, 1. You get that? In fact, whenever y is equal to 1, on all this entire line, whenever x is equal to 1, so on this line, f of 1, y is always 0, 1, 1. So on this line, every vector is going up by 1. When you have x equal to minus 1, for any y, this is 0, minus 1. So on this line, every vector is going down like this. X is equal to 2, no matter what the y is, you're always going up 2 units. Right? So this vector field has a picture that looks less than, it's a little bit more clearly drawn and with more examples in the text on page 1090. It's in the text that I have. Let's look at another example. Well, this example A. This is example 1, set of examples. Next. Suppose we take f of x, y, the vector field, to be 1 minus y squared, 0. By the way, why is this called a shear field? Sort of like you're forcing, like if this were a piece of material, it's like the side's being forced up and the other side's being forced down. So it's like a shear force. That's really what's going on. If you look at this picture, this is called, this is 1 minus y squared for y between 0 and 1. So this is not negative. So this vector field is only defined on the strip when y equals 1 and y equals minus 1. So it can depend on what the x is. This has the same values for all x, right? Because you don't see a y over here. So f of when x is equal to when y is equal to 0, f of x y, f of 0. That means on the x-axis, right? These are all the points x0. F of x0 is 1, 0. So on the x-axis, at every point, there's a vector pointing horizontally to the right of length 1. When you're at the edge, when y is equal to 1, f of x1 is equal to 0, 0. It's the edge, just the 0 vector. What about halfway through? F of x1 half. When y is a half, this is 1 minus a half squared, 0. When a half squared fourth, this is 3/4 comma 0. So in this line, at every point, there's a vector of length 3/4. And this is the case whether you have plus or minus a half, because you're squaring y. So on this line, and as you get closer and closer to the boundaries, so if you think of this as describing the flow of a fluid, this is a channel, and the water is flowing through the channel, but at a certain high rate in the center and decreasing it go towards the boundary, and at the edges, the water's not moving at all. It's still. So you can think of like if you were to look at a flowing very fast in the center and getting more and more slow, moving more and more slowly as you get to the edges. So this is sometimes called channel flow. You can think of this as water flowing down our channel. These are the boundaries of the channel. The third example is what is sometimes called a rotation field. So if we take f of x1 equal to minus yx. So this is very interesting, or this is, if you want to write it in terms of j components, minus yi plus xj. This is called a rotation field, and it looks like fluid or something going around in around and around and around. So let's see. So at the center, f of 0, 0, 0 is just 0, 0, 0. F of 1, 1, 0 is 0, 1. So here, the vector is be straight up. F of 2, 0 is 0, 2. F of 3, 0 is 0, 3. What about it over here? What about the y-axis, the positive y-axis? F of 0, 1, let's see, x0, y is 1, this is minus 1, 0. So it's this. F of 0, 2, y is 2, x0, minus 2, 0. F of 0, 3 is minus 3, 3, 0. Just like that. What about down here? f of minus 1, 0 is 0 minus 1. That's going straight down 1 unit. F of minus 2, 0, 0 is 0 minus 2. And f of minus 3, 0 is 0 minus 3. Looks like. And on the negative y-axis, when f is 0, y is minus 1, or 0 minus 2, or 0 minus 3, x 0, y equals minus 1, 1. This is 1, 0. This is 2, 2, 0. And this is 3, 0. These vectors look like this. What about a point like this? What is f of 1, 1? F of 1, 1 is minus 1, 1. So at the point 1, 1, we're going like this. F of 2, 2 is minus 2, 2. Looks like. So forth. What about f of minus 1, 1? F of minus 1, 1, when y is 1, and x is minus 1. So at minus 1, 1, you have this vector. What about at minus 1, 1, minus 1? F of minus 1 minus 1 is 1 minus 1. So 1 looks like this. It looks like somehow, if this is described, if the vector field describing the motion of a fluid at every point in the plane, it looks like the trajectories are sort of going around in a circle, kind of. It's like the water is flowing around. That's why this is called a rotation field. So these are three examples of vector fields. And again, a radial vector field is a vector field f of xy, which is equal to the x vector at y and something which is proportional to, it's like this is a special kind of radial vector field. So xy, or this is where r is the vector xy. That's a radial vector field. Let me look at two examples of radial vector fields. Suppose we take p equals 1, 1. So in this case, my vector field, f of x, y, is the vector divided by the vector. This is just a unit vector, a vector of length 1. So at every point in the plane, of length 1 in the same direction. Oops. This is, yeah, that's right. In the same direction, but of length 1. So when p equals 1, it's assigned to every vector a unit vector in the same direction. And when p is equal to 3, this is really very interesting. It comes up infinitely often, science, physics, engineering, chemistry. The vector field F is equal to the vector divided by the length of the vector cubed. The cube is a little tricky. This means 1 over the length of the vector squared is the vector divided by its length. So this is really an inverse square law. This is a unit vector in the direction of r divided by the square of the magnitude of r. Right? So this is an inverse square radial vector field. So this is the vector fields. These are what we study for the rest of the semester, which is really just 2 weeks. But this is really what we're doing now in chapter 17. Now, this is example 2. So let's C be the skull. X squared plus y squared equals a squared. A positive. So this is just the circle on the plane. And consider the radial vector field. F of x, y equal to r over the length of r. Or in terms of x and y coordinates, r is vector x, y, and the length of x, y is square root of x squared plus y squared. And we want to, so at any point on the circle, we have a vector in the same direction, but a unit vector in the direction. This is our vector field. The circle C is this. And we're asked to show that at each point of C, that means every point on the circle, the radial vector field which is divided by the length of r, is orthogonal, which means perpendicular, is orthogonal or perpendicular to the tangent line C at the point. So the tangent line, here's a point, here's the tangent line in green. And we want to show that these two are perpendicular. So one way to do this is to recall a basic theorem about vector fields. Which is the following. Another call. So this is the text theorem 15.2, chapter 15, section 5, which says the tangent line the little curve of the function f of x, y at a point A, B is orthogonal to the gradient of f at AB, so long as this gradient is different from 0. So let's recall what that means. Suppose we have a function z e f of x, y, and point AB that says f of AB is equal to some numbers. So we have the level curve f of x, y equals c. Right? So in the plane, we have some curve, and these are all the points where f of x, y equals c. In particular, the point AB lies on that curve. So f of x, y equals c. So we describe the curve by some function r of t with coordinates x of t, y of t. So at any point on this curve, every point at xy is x of t, y of for some t. And f of x of t, comma, y of t, that's a point on the curve. So when you evaluate the function at that point, of course, it's equal to c. So as a function of t, function is constant. A constant function has derivative 0. So the derivative with respect to t of f of x of t, y of t is equal to 0. But by the rule, derivative of f of x of t, y of t with respect to t is the partial of f with respect to x dx dt plus the partial of f with respect to y dy dt. This is the dot product. Partial f with respect to x, partial f with respect to y, with dx dt, dy dt. But the partial of f with respect to x, comma, partial f with respect to y, that's just the definition of the gradient of f. Dx dt, dy dt, that r prime of t. So r prime of t is the tangent vector. And this says that tangent vector at any point on the curve has dot product 0 with the gradient, which means the gradient is perpendicular to the tangent vector. Right? So that's the fact that we proved in chapter 15, and we use a lot from now on. So let's go back to our picture. We have the circle, x squared plus y squared equals x squared. We have a function of xy, the radial vector field, r over the length of r. And if you look at x plus y squared equals a squared, C, the level curve of the function f of x, y is x squared plus y squared. It's all points where f of x, y equals a squared. So C is the level curve of this function. So the gradient f is what? The gradient of f of x, y is the partial of f with respect to x, I plus partial of f with respect to y, a. Partial of f with respect to x is 2x. Partial with respect to y is 2y. This is the same as 2 times x I plus yj. So the gradient of f of y, which is a vector valued function, is this. And so at any point, this is really 2, let's say 2r, right? So the gradient of f of xy is really a multiple of capital F of x, y. It points in the same direction. Capital F of x, y, this vector field, I can write this as 2 times the length of r times r over the length of r. So this is 2 times the length of r, f of x, y. So the gradient of f is parallel to this vector field. The gradient of f is, by the theorem we just proved, orthogonal or perpendicular to the tangent vector at every point on the curve. That's what I wanted to show. So the example 2a, and this is worth looking at in some detail to sort of understand what it says. Suppose we take the rotation vector, or a multiple of the vector field that I called the rotate vector field a moment ago. G of x, y equal to, so the first example of a rotation vector field was just minus y comment. But let me just divide that by the length of the vector, square root of vector of x plus y squared. So if I call, remember the circle C is the level curve of the function x squared plus y squared. It's all points where x squared plus y squared equals a squared. So, and what is the gradient of f? This is f of x, y. I already calculated the gradient. This is the gradient. The gradient of x, y, dot product with this vector field is what? The gradient of f of x, y is 2x, 2y, dot product with minus y over square root squared plus y squared. denominator can come out x squared plus y squared. The dot product of these two vectors is 2x minus y is minus 2xy plus 2y times that, or 2xy. These cancel. This is 0. So the gradient of f is perpendicular to vector field g of xy. But the gradient of f of xy dot product with the tangent vector, this point, is all 0. So this vector and this vector both perpendicular to the gradient. So let me draw a picture. It's like here you have the gradient, and your two vectors perpendicular to that. And the vectors are perpendicular to the vector, parallel. That means. Now, one way to get a vector value function, one way to get a vector field is if we start with a vector value function a scalar value for function of xy. So this is a function of two variables, scalar value function. We can get from phi, we can get to the gradient of phi. Gradient of phi is by definition the partial value of phi with respect to x, comma, a partial value of phi with respect to y. So in the example we just saw, add the function phi of xy equals x squared plus y squared, then the gradient of phi is 2x, 2y. And this is a vector value function. Every vector x, you end up with a vector. And if a vector field f is the gradient of a vector of a scalar or of a scalar value in a function of two variables phi, then f is called a gradient field, and phi is called a potential function. Again, if you've taken physics and you study, for example, like electromagnetism, there's the electric potential, and you have the electric field. And in physics, if you have the potential, if you have a potential function, it's gradient in an electrical field. Right? Gravitational potential and gravitational field, magnetic potential, magnetic fields. Those are just instances, but none of which you don't need any physics to talk about what we're doing. But you do have to know these definitions. If you start with a scalar valued function phi, you take its gradient, you get a vector field. And that scalar valued function phi is a potential function for the vector field, which is called a gradient field. Let's take another example. if phi of xy is just x times y, then the corresponding vector field of f, which is the gradient of phi, if you differentiate with respect to x, you get y. If you differentiate with respect to y, you get x. So the potential function associated with this gradient field, gradient field associated with this potential is y comma x. Let's look at some more examples. This is a new topic for us and takes some while to figure out everything that's going on. This is example 4. Suppose we take temperature function. So suppose we have, let's say, a circular plate. It's a disk, a radius 5. So this is, we're not looking at the circle, we're looking at the whole disk. So this is all points x, y, where x squared plus y squared is less than or equal to 5 squared, or 25. Right? So this is region R. R is the set of all points x comma y, such that x squared plus y squared is less than or equal to 25. And suppose that every point on plate, you can measure temperature. The temperature T at any point on the plate is 200 minus x minus y squared. So to vector xy, so this is real T of xy. Every point xy, you get a number, the temperature is a scalar. So this is a function of two variables. What is the gradient of T? If you differentiate this with respect to x, you get minus 2x. If you differentiate this with respect to y, you get minus 2y. So this is a vector field. This vector field has this potential function. This is a gradient field. Right? At any point y, value of the vector you get it by the value of this vector field is the gradient of t at x, y, where t is the scalar of a value function. Right. So this is minus 2 times xy. So this means is that at every point, this is a radial vector field. This is scalar multiple of the vector. So every point, you have a vector in exactly the opposite direction, pointing towards the center disk. And as you get closer and closer to the center of the disk, your vector gets smaller and smaller in length, or it's proportional to the length. So the length of the vector decreases, so does these little arrows. So the heat distribution if this is the temperature at every, the flow of temperature is in this direction. So the bigger so this is always, so at any x, y, at any vector, your vector field is a vector pointing in exactly the opposite direction. That is instead of away from the center towards the center, and it's minus 2 times the length of the vector. So as the vector gets smaller and smaller. So there's this temperature flow. And if you think of this as measuring the temperature at every point on the disk, when X and Y are both 0, temperature is 200. That's the maximum. The hottest point on this disk is at this here where the temperature is 200. When you're on the boundary of the disk, where X and Y, X squared plus Y squared equals 25, this boundary, the temperature is 175 degrees. As you go, and at the center is 200 degrees. So as you go in towards the center, the temperature is increasing. The hottest part of the temperature is at the center, and the temperature decreases as you move to the edge of the disk. And if you think heat flowing from high temperature to low temperature, then the heat will be flowing in the direction towards the edge of the disk. Exactly the opposite direction of the gradient function. Let's look at another example. This is example A in example 4. In example B, we have a potential, it's called a velocity potential. Potential is the function phi equal to the inverse tangent of xy, or sometimes people like arcgent of xy. My scalar valued function of two variables. So my vector field F is the gradient of phi. What is this? A derivative of the inverse tangent of x? It's 1 over x squared plus y squared. So by the chain rule, if I differentiate this with respect to x, I'm going to get 1 plus xy squared y squared in the denominator, and times the derivative of xy with respect to x, which is y. I get y over 1 plus x squared. And when I differentiate this with respect to x, I get x over 1 plus x squared y squared, which, well, that's what it is. What does this gradient field look like? So so if we take phi be the inverse tangent of x and y, what are the level curves of phi? These are all points where phi of xy is some constant c, or the inverse tangent of xy, some constant c, or just tangent, the tangent of x, or xy is equal to the tangent of c, which I'll capital C. What is this? This is a hyperbola. Xy equals c is positive. It's a hyperbola. It looks like that. If c is negative, it's a rectangular hyperbola that looks like that. But the level curves of this function are hyperbola. And the vector field is all orthogonal to the level curve. So the vector field, the gradient, right? This was the theorem that I proved from chapter 15 a little bit earlier. The gradient of a function is always perpendicular to the level curves of the function. So these are the level curves, and the gradient, the vector field, is always perpendicular to this. Sometimes so if phi, this is just to introduce some terminology. So if phi is a potential function, then the level curve phi of x, y equals c is also called equi potential curve, because it's all points where the potential function are equal to c, an equal potential curve. And this is just if you're looking at the book and you'll see this expression being used, and now you know what it is. So since we're introducing these new vector fields today, I'm spending a lot of time with examples and drawing pictures, and let's then continue. So this is example 5. Suppose we take the potential function e of x, y equal x squared minus y squared over 2. Then the gradient field, which is the gradient of e, is what? If I differentiate this with respect to x, I get 2x over 2, which is x. If I differentiate this with respect to y, I get minus y over 2, which is minus y. So this is the gradient field. What is the equal potential curve? At the point 2, 1. So phi of 2, 1 is 2 squared minus 1 squared of 2, which is 4 minus 1 is 3 halves. So the equal potential curve is all points where phi of x, y equals 3 halves, or x squared minus y squared over 2 equals 3 halves, or x squared minus y squared equals 3. This is a hyperbola, right? When y is 0, x is the square root of 3. When y is 0, or minus the square root of 3. And when y is 0, and you get a hyperbola that looks like this. What is the gradient of phi at the point 2, 1, or f of 2, 2, 1? f of 2, 1 is 2 minus. So the 0.21 lies on this curve, right? Yeah, of course. When x is 2 and y is 1, this we have. So this is the point 2, 1. And at the point 0.21, the vector field is 2 minus 1 over 2 down 1. And so the value, so and this, we have the function xy equals x squared minus y squared over 2. That's a scalar valued function. If we get gradient, we get a vector x minus y. So for this vector field, this is a gradient field. It's the gradient of a function phi, and phi is the potential function for this vector field. The equipotential curve at 2, 1, it's the level curve where phi of xy has whatever value the function is at 2, 1. When x is 2 and y is 1, this is f. So the equipotential curve is this. Was a parabola. It's all the points where x minus y squared equals 3. So, and at the 0.21, the gradient, the value of the vector field f is 2 minus 1. What is this, the tangent vector? At this curve. So the curve is given by x squared minus y squared equals 3. And see whether there are different ways I can just let me see which way the book seems fair. Let's see if we can do this by implicit differentiation. Let's just differentiate this with respect to x. So this is from Calc 2. Implicit differentiation. If I differentiate with respect to x, squared minus y squared, I get 2x minus 2y dx. But x squared plus minus y squared is 3. This is the same as the derivative with respect to x of 3, which is 0. So this says is that 2x equals 2y dx, or dy dx is equal to x over y. So at the 2, 1, dy dx, it is 2 over 1, 2. And so the tangent line here has slope 2. And after 2 minus 1 has slope minus a half. And 2 times minus a half minus 1. And you should have learned when you're studying lines, the two lines are perpendicular. This is minus 1. The product of their slopes is minus 1. So again, in this example, there's a lot to think about. That's all I can say. Okay. So this is the first thing that you study in vector fields. What is a vector field? And very special vector fields that are gradient vector fields that come from taking the gradient of a function of two variables. Now, gradient is something like a derivative. Let's try and get something like integral. And there's several integrals one can imagine. But this is section 17.2. This is something called a line integral. And the idea is the following. You have some curve in the plane. So C is a curve. Given by R of t equal x of t, y of t. Let's say t is from A to B. This is R of A, and you end up at R of B, and we assume it's a smooth curve, which means these functions can be differentiated. They're nice functions, and it's finite length. It's a curve on a finite end. And we want to define, and we have, and then we also have a function. So we have a scalar value function. It's not a vector value function. It's a scalar value function. Z equal f of y. We wanted to find something which will be a scalar line integral, which will be the integral along the curve C of the function f of xt, y of t, dt. Or we sometimes simply write this as the integral of ds along C. So we have a function, and we want to integrate the function along a curve in the plane. So this is something new. And the way we're going to do that is very similar to how we define an integral in beginning calculus. You have your curve, and you divide it up into small pieces. And you consider the distance along each of these. When you approximate these little curves, but the chords, the lines connecting the points along this curve. And if each of these lines length, so let's call it delta S. Okay, this is the K that looks along this thing, and you evaluate the function at some point in this piece. So let me say this a little bit more carefully. So we have the interval t going from A to B. From this t, every t in this interval have r of t. We get to get this curve. So let's take the interval from A to B and divide it up into pieces, just the way we did in Calculus. T0, T1, T2, say B is T sub n. So we have n pieces. And in here, let's say it is T sub k, and the preceding point is T sub k minus 1. So on the curve, you have S of T sub k minus 1. A little further along, S of T sub k. And the length of this arc, we'll call delta S of k. So this is the length along the curve from this point to this point. And pick in the interval from tk minus 1 to k, you pick some point sub k called T sub k star. And so here we have S of T sub k star. We evaluate the function at that point. Actually, this is really, sorry. This is R of tk, this is R of T sub k minus 1. And delta sk is this arc length. We use S for arc length. So this is F evaluated at X of T sub k star, Y of T sub k star. So this number times the length of the interval delta S sub k, that's something like the line integral from this point to this point. And we sum this up over all the values of k from 1 to n. And this is an approximation to what we want to call the line integral. And we take more points of subdivision where these small pieces of arc have smaller and smaller and smaller. We take the limit as the S sub k goes to 0. And if this limit exists, this is what we call the integral along the curve C of the function f ds. So we'll find out in I guess maybe on Monday, efficient ways to do this calculation. But this is the definition of a line integral along a curve, completely analogous to the definition of an integral in Math 175. And in fact, when your curve is simply a piece of the axis, this is exactly the same thing. So maybe very quickly, I'll give an example or method to evaluate a line integral. So you get to see it before the end. But if you have a curve, R of t, from A to B, and if you take some point t along there, the arc length, S of t, which is arc length along the curve from R of A to R of t, this is equal to the integral from a t. This is an arc length formula that we've seen. R prime of u, the absolute value, the square root of x. This is exactly the formula for arc length. This is integral from A to t. Square root of x prime of t squared plus y prime of squared dt. So the formula for arc length. And the integral along the curve C of a scalar valued function f ds is the integral from a to b of f of x of t y z absolute value r prime of t dt. This is sort of like this is like ds. Let me see if we can actually do an example. So suppose we have the disk of radius 1, x squared plus y squared less than or equal to 1. And we have a function on this. Let's say this disk has been heated and there's a temperature. So the temperature between x, y is going to be given by, in this example, 100 times x squared plus 2y squared. So this is a scalar valued function. And we want to find the average temperature around the boundary of this disk. We're taking the curve C to be x squared plus y squared equals 1. So we take r of t to be cosine d sine t, and it goes from 0 to 2 pi. We go once around the circle. So the circle C equal x squared plus y squared equal 1 is parametrized as usual in this way. So the integral along the circle of the function t ds, let's use this formula. This r of t, what is r prime of t? R prime of t is minus sine t cosine t. This is another point on the unit circle. The length of this is 1. So if we use the formula that this is t of x of t, which is cosine, comma y of t, which is sine t, this is 1 t from 0 to 2 pi. This is the integral from 0 to 2 pi of 100 times cosine squared t plus 2 sine squared t d. So this line integral is this, which is to be calculated. Cosine squared plus sine squared is 1. So this is the same as 100 times go from 0 to 2 pi of 1 plus sine squared t dt. And this is something which you should have learned how to do in Calc 1 or Calc 2, and maybe I'll do it on one day, but this is just an example. This is the formula to allow you to calculate a line integral. And this is the key thing you're going to use a lot. So this is the integral of a scalar valued function along a line. And the second kind of line integral, which we'll learn, we'll see it all, is how to do the line integral of a vector field along a line. And these are the two ingredients that we'll need when we see conservative vector fields, which are vector fields that are radiant fields, and Green's theorem. Okay, so we have a lot to do in the next couple of lectures, but what you really need to be studying, and as much as you can do this on your own before each class, the better prepared you are for a class. Is we're doing section 1 through 4 in section 17. And the culmination of all this is Green's theorem. You might say, in a certain sense, the whole of this course is to learn the statements, the two forms of Green's theorem, the states and of Green's theorem, what they mean, and how to use them to solve things. Okay. Any questions about this? Yes, as I do. But it really is amazing, the most interesting part of the course. So we've gotten to a nice place. If not, enjoy the day. And if you have questions, I encourage you to come to Zoom sessions today and tomorrow. Any time we can arrange it at your convenience. Otherwise, see you on Monday. Okay. Bye all.